Hey, welcome back to Fat Mama Physics! In this video, we are going to go over another tension problem, and specifically, this is what we call Atwood's machine. Some applications of Atwood machine is, in the old days when elevators were made, you needed a counterbalance. Let's explain this a bit. You got two masses, they're attached to a rope, they're hung over a pulley, and there's another mass attached to the other side. So if apply to an elevator back in the old days, you walk on the elevator on one side, and then in order to pull this elevator up, you need a counterbalancing weight on the other side to pull it down, or to slowly let the elevator come down, or if the elevator were to fall or anything, you have a counterbalance weight on the other side just to make sure to keep this other mass here in check. One difference between your Atwood's machine and the previous problem where you had two masses attached to a rope and pulled in the forwards direction is instead of the acceleration going forward, it's now looped around a pulley. The pulley has a function of changing the direction of motion of your objects, or in our case, our system. So let's analyze these two masses that are hung from a frictionless pulley, so we don't have to consider the friction that would act on the rope, which is not true. It's in reality is there, and assume this pulley is massless, and these two objects are released from rest. We want to find the acceleration of our system. And this is all the information we are given. So let's think about it. If you were to let these two masses go, what do you think will happen? Yes, if you are thinking these masses are this guy, the 6 kilogram mass, is going to come down and the 4 kilogram mass is going to go up. Yes, you're right, since the 6 kilogram mass is heavier. So now we've determined the direction of our acceleration, which is up on this side and over the pulley down on this side. That's one of the important steps. The next step we're going to do is we are going to draw our free body diagram, which for the 6 kilogram mass, we have the force due to gravity. I'm going to label that 6, by the way. We also have the force due to gravity acting on the 4 kilogram mass. Now, both of these masses are tied to a common string, a rope connecting them. So we have the tension force acting towards the center of the rope for this guy, and which the tension force will be the same, equal in magnitude, for the 4 kilogram mass, also pulling on the mass upwards. Now this is where it gets a little bit funky, because when we determine the positive direction, notice the direction is looped over a pulley, which means that any force that points along this loop is going to be in the positive direction. Any force that points against this loop backwards will be in the negative direction. For example, this force of gravity acting on the 4 kilogram mass is pointing against that loop, against that direction of acceleration. Therefore, it must be in the negative direction when we use it in our F-net equation. So let's do that right now. I'm going to choose the whole system, both the 6 kilogram and the 4 kilogram mass as my system. That means I get the 6 kilogram mass and the 4 kilogram mass as my M in MA. If I take a look at all of the forces acting on our system right here, notice I drew a little pant-looking thing just to show that our system is looped around the pulley. I have the forward force, so pointing along this direction of acceleration. That includes FG6. It also includes this force of tension here, which also points along this direction of acceleration. Acting against the direction of my acceleration is this tension force, which pulls upwards, which pulls opposite to the direction of acceleration. More importantly, I have this FG4 acting on this mass that points away from the direction of acceleration, which is up on the other side. And you are thinking, okay, why don't you just cancel the tension forces? Yes, you are right. I could have just ignored them since they were all this because it was an internal force inside my system. And we are left with Fg6 minus Fg4 equals to our mass of our whole system times acceleration. Intuitively, it makes sense because Fg6 will drive the acceleration, Fg4 will hinder the acceleration, hence the minus sign. So we know that Fg is mg. We can then substitute mg into our fg's over here, in which the m's are going to correspond to whichever mass we're talking about, and g is just acceleration due to gravity, 9.81 meters per second squared. So let's substitute, let's change that here. Since we're solving the acceleration of the system, solving this A, I'm going to divide the whole thing by 10 kilograms first. And I got a little lazy there with the units, but let's put in G and finish this off. 1.962. Notice that's just 2 times G if you just subtract it. So then this is going to round to 2 sig figs, giving me, that rounds us up, 2.0 meters per second squared down on the left side, just to make sure we specify direction there. Okay, so notice that the difference in the Atwood's machine is the direction of acceleration is now looped around. It's a curvature instead of a straight line. Now for B, we're going to find the tension in the string for the Atwood's machine. Again, in this one, it really doesn't matter which one you choose to find the tension in your string. Either mass, that's your system, is going to work. But I will do it both ways, just so you can see them both. So for the 6 kilogram mass, we have the following free body diagram, in which this mass, the direction of acceleration is downwards, which I will choose as our positive direction. So now I'm going to write our F-net equation. And our F-net is going to be Fg in the positive direction minus our tension force in the negative direction. I am going to solve for the tension force. We know Fg is just mass times gravity, so let's substitute that in as well. And here we can put everything in where the mass is going to be the 6 kilogram mass, acceleration due to gravity, and acceleration is 2 meters per second downwards, which I will put in as positive since I've determined downwards to be my positive direction. And then I'm going to use that instead, 1.962. Okay, I get 47.088. Rounding up to 2 sig figs, 47 newtons. So let's do the other mass just to show you what that's like. But this time the acceleration is upwards for the 4 kilogram mass. So Ft is going to be positive, not Fg anymore. So upward force, we have Ft, subtract the opposing force, Ft in the Fg in the opposite direction, equals the 4 kilogram mass times its acceleration. So then let's solve for the tension force. And we know Fg is just mg. Substituting in our mass for 4 kilograms and acceleration as this 1.962 non-rounded number. And we also get 47.088. So there is no difference on whichever mass you use as your system. Both will yield the same answer for your tension force in the system. But the key thing is to pay attention to which direction is your object accelerating and determining and making sure the signs, the positive and negative signs, are consistent in your F-net equation. Here I have a very identical question for you to try, in which I just changed the masses on the Atwood's machine. So this is a good time to pause the video and for you to try the problem. And now it's my turn.
Drawing our free body diagram. First, we have gravity acting on both our weights, force of tension acting upwards, in which they will cancel. Acceleration is down on the right. We're writing our F-net equation. Our mass is both our masses for the entire system. F-net is down on the right, and the Ft's cancel, so we have Fg8 minus Ft3, which is opposing the direction of acceleration. Here we are solving for the acceleration, in which the force of gravity Fg is going to be mg first of the 8 kilogram mass minus Fg of the 3 kilogram mass, all divided by the total mass, giving us 4.45-ish 4.5 meters per second squared down on the right. Solving for tension, we can use either mass. So I'm going to do one at a time. For the 3 kilogram mass, it will accelerate upwards. So for the net equation, it will be Ft minus Fg. Ft is upwards. So solving for Ft, we get Ma plus Fg. Fg is just mg. And solving for the Ft with the 3 kilogram mass, we get 42, which rounds up to 43 newtons. So doing the same thing for the 8 kilogram mass, drawing our free body diagram for that one. This time acceleration is downwards on the right, which Fg is going to be positive and Ft is opposing it. Solving for Ft here, we get Ft is equal to mFg minus ma, in which Fg is mg, and for the 8 kilogram mass, we get something similar, 42.8, rounding up to 43 newtons.
And here are the solutions to this problem that you've just tried. The only difference is that you have the heavier mass on the right side instead of the left side, so your acceleration is down on the right. Otherwise, every other step is pretty much relatively the same. Okay, great. So hopefully you learned something from this video that you can apply in your practices. I wish you good luck. Thank you for watching this video. Fat Mama Physics signing out.